electricity. Hey there, science explorers. Do you ever wonder why your hair sticks to the balloon after you rub it?
Or why lightning cracks across the sky during a storm?
Well, get ready for a shockingly cool adventure because today we're diving into the electrifying world of electric charge.
Yup, it's that invisible force that makes our gadgets work and sparks some serious cool science magic.
So grab your safety goggles and let's plug into the electrifying journey of electric charge, where sparks fly, electrons groove, and science gets supercharged. Hey Alan. Come on, man. We can't be caught lacking like that.
Sorry. Alright, let's go back to where we started. You see, all these phenomena can be explained by a basic property of matter known as electric charge. Electric charge is a fundamental property of matter. It is carried by elementary particles such as protons, electrons, and governs how charged objects are affected by an electric field.
Zain, focus up, man. We got an assignment to do.
Come on, man. You can't even let a man eat his banana in peace.
Just focus up already, come on.
Fine, where were we? Okay, so when these charged particles enter an electric field, they experience a force known as the electrostatic force. The electrostatic force, also known as Coulomb's force, is a force of attraction or repulsion between two charged particles. We can actually determine the magnitude of the electrostatic force by using Coulomb's law, which we will explore later on. Now, before we dive deeper into electrical charges and Coulomb's law, we must first take a look at the subatomic level. It is crucial to understand the electrical structure of matter so that we can fully understand how electrical charges work. Here, we have an electron in the color blue, and here we have a proton in the color red. Now, both of these subatomic particles have an electrical charge. The single proton over here has a quantized positive charge, while this electron over here has a quantized negative charge. Now, the magnitude of both of these charges is the exact same. However, the electron has a negative charge, while the proton has a positive charge. And the calculations for this magnitude come to be somewhere around 1.602 times 10 to the negative 19th.
To understand how these subatomic particles create charges in objects, let's look at the structure of an atom. Here, we got the model of a beryllium atom. Inside, there are protons, which are positively charged. And outside, we have electrons, which are negatively charged and rotate around it. Now you see the outermost shell, it's a valence shell, which means that the electrons can freely move from one atom to another, which create charges.
Now, instead of having a deficit of electron, now we have an extra electron. So the nucleus still has 4 protons. However, the entire atom now has 5 electrons. Since we have that one extra electron now, the entire atom now has a net negative charge, since that one extra electron is going to offset the entire positivity of the nucleus. Okay, now we're going to try a real-life demonstration on how valence electrons in atoms can help create electric charges.
First off, you can see how the balloon does not attract any part of my hair. But as soon as I rub it, you can see that the hair starts to stick up and start to attract to the balloon.
So what's the physics behind this? Basically what's happening is that the electrons from Alan's hair are getting transferred into the atoms of the balloon. This causes the balloon to have an overall negative charge and Alan's hair to have an overall positive charge. If you remember elementary school classes, opposites attract. Therefore, Alan's hair is now attracting the balloon. I'm not sure if you do.
Now to further analyze what actually happened in the hair balloon experiment, we have to dive deeper down to the molecular level. As the balloon rubs against your hair, it picks up electrons from your hair. And what that does is makes the balloon into a net negative, while your hair becomes net positive. Now, that's why when I hover the balloon above my hair starts to stick up, because opposites attract.
Now, what really happened there was that the valence electrons in Alan's hair, they felt more attracted to the balloon, so they transferred from Alan's hair to the atoms in the balloon. Okay, so we talked a lot about what electrical charges are. Now, let's touch upon how we can calculate the magnitude of the electrical charge. For that, we use the formula Q equals NE. Now, let's break this formula down. Q is the total amount of charge in coulombs. Q equals NE. N is the total number of charged particles. In this case, that could be an electron or a proton. And E is a constant. And we touched upon this before. Would you like to remind us what the constant is?
Of course, 1.602 times 10 to the negative 19.
Bingo. That is the constant for the charge on a single electron or proton or a charged particle. So, using this formula, we multiply the number of electrons with the constant for the charge of a single charged particle, and by multiplying those two together, we get the total amount of charge of that object or whatever we're talking about in coulombs. Now that we know all about electric charges, we can now better understand how electric charges can come together to form the electrostatic force. When two charged objects come near each other, they form something known as the electrostatic force. The electrostatic force is the force of attraction or repulsion between charged particles or objects. To better understand electrostatic force and how we can determine it, we will now explore Coulomb's law. Alright, now let's take a look at the mathematical representation of Coulomb's law. Now this equation that I have up on the screen is known as Coulomb's law. As previously discussed, this equation is used to describe the electrostatic force between charged objects.
Based on pre-existing information about charges, like how likes repel and opposites attract, the law states that the electrostatic force between the two charges is K Q1 Q2 all over R squared.
Now let's break down each one of these variables to get a better understanding of how we can use Coulomb's law to determine electrostatic force. First off, we have Fe, which is the variable for electrostatic force. Ke is Coulomb's constant, also known as the constant of proportionality. Ke equals 8.99 times 10 to the 9, and the units for it is Newton times meter squared over Coulomb squared. Next, we have Q1 and Q2. Now, Q is the variable used to represent electric charge, and it is measured in the units coulombs. Now, if you see here, we have two objects, Q1 and Q2. Each one of these objects has a charge. The charge that these objects have are the ones we use in our Coulomb's law calculations. The last variable that we have is R, which is the distance between the two objects.
Now, this may be familiar to you. This is identical to Newton's gravitational law. The only difference is the constant, and that gravity can only attract. Coulomb found that the forces between the two charges is proportional to the charges Q1 and Q2, and inversely proportional to the distance between them squared.
Now that we know what each variable means, we can now get a better understanding of Coulomb's law and how we can use it to determine electrostatic force. To summarize, Coulomb's law states that the electrostatic force is equal to the product of the two charges times the constant of proportionality, also known as Coulomb's constant, divided by the square of the distance between the two objects.
In conclusion, we talked about how electric charge is a fundamental property of matter that describes the presence of electric force. There are two types of electric charge, positive and negative. Like charges repel and opposite charges attract. We also talked about the electrical structure of matter and looked at the atom's structure, along with explaining how atoms ionize when they lose or gain an electron. So that is for our video. Hope you enjoyed, and we'll see you next time.
You mother. Alan's here, which neutrally. Stop laughing like that. It was fine if you did that. It was too funny. It was too funny. You can't even blame me.